Well, it's for me a special occasion here to thank Alan, simply because I did my PhD under his supervision and I was his first PhD student. I will talk a little bit about that and then we'll move to the satellite lines, which have been extensively discussed already. So I got an ESRO fellowship to join the Callum laboratory where Alan was working, and there he proposed to work to develop an electromagnetic shock tube to study a high-density effect in helium plasmas, the so-called plasma polarization shift, an effect due to the concentration of perturbing electron on the emitting ion, which resulted in a blue shift of the resonance line. This effect had been studied by Grimm and co-workers, and at the time of this experiment that led to controversial results, both in theory and in experiment. So what we did was to produce the hydrogen-like helium resonance line, Lyman alpha, beta, etc., up to n = 4. And we did the first measurements of these 4 lines and the shift measurements. The shifts were indeed confirmed to be to the blue side as suggested by theoretical considerations. And, but the agreement in terms of quantitative agreement was only possible with a quantum treatment developed by Grimm using hydrogen continuum wave functions for the perturbing electrons. Now, since these effects were produced in high-density plasmas, we talk about densities of 10 to the 18 electrons per cubic centimeters, we also considered the possibility of having these perturbing electrons trapped in highly orbitals, corresponding to, in fact, hydroelectronic satellite effects. And it was shown that under these high-density conditions, these lines would be totally negligible. So the only explanation for the shift was really due to plasma polarization. And this led to a number of publications joined between Alan and myself, and was the subject of my PhD. Okay, so while this work was being done under his supervision, Alan, of course, was concentrating on a laboratory spectroscopy, in particular using the theta pinch machine to produce spectra to be compared with solar sources. And it's also at the time that he developed the theory of the dielectronic satellites. And the seminal paper was just mentioned by Ken in his presentation. So he showed that the production process of these satellite lines was dielectronic recombination. So due to a free electron being trapped in the parent ion in highly excited state and forming autoionization, doubly excited states, which from which the satellites were produced. He showed also that the intensity ratio between the satellite lines and the parent resonance line was definitely temperature dependent, essentially temperature dependent, and dependent on the transition probability of the resonance lines, which scaled as z to the 4, showing that these lines would be much more important, more intense in heavy ions. Now, this was not mentioned, but Alan developed a theory of the inner shell satellites, which were produced in the recombined ion from inner shell collisions, and which also led to some satellite lines, which were originating from doubly excited state, which were not autoionizing. And he showed that the intensity ratio of those lines were dependent on the abundance ratio of the parent to the recombined ion, and also on the ratio of the collisional rate coefficient. So this offered another diagnostic capability with regard to the ionization state of the plasma. Okay, the early work was devoted to the redshifted lines originating from n equals 2, the so-called the quantum number of the parent of the perturbing electron. And these calculations, indeed, were first confirmed in '72 with a spectrum which had been taken from the Intercosmos 4 satellites by Grineva et al. And showed really the fit of these n equals 2 satellites with the observed spectra. Now, in the period after 72, 73, Alan took the next step to improve the diagnostic capabilities by extending the work to include satellites coming from levels with n larger than 2 for helium-like and then later for hydrogen-like ions. This, of course, entailed the calculation of a very large number of atomic parameters, autoionization rate, transition probabilities, collisional rate, and so on. And this work was realized through a collaboration involving the atomic physics group at the Nice Observatory with Françoise Bailly-Dubois, Paul Fauché, Lois Stenman-Clark, and Meudon, Jacques, Dubois, Michel Luller, and later on Marguerite Corny, and myself in Mons. A series of workshops were held regularly at Nice, mainly at Nice, but also occasionally in Meudon and Callum, and to discuss the progress of this work. And the early result of this activity were devoted to the study of n equals 3 satellites in the iron-25 spectrum. And it was shown that those satellites, which appeared very close to the resonance line, were of importance in order to improve the diagnostic capability of the method. Here is a picture showing one of these gathering at the Nice Observatory. You see Alan, which looks a little bit skeptical there. I don't know why. With Françoise, Jacques, Lois Stenman-Clark, Michel Luleg, and myself. This picture was shot by Paul Fauché, and then this picture was shot by Alan with Paul here, standing there. So throughout this activity, the collaboration worked to prepare all the atomic parameters that were needed for the solar maximum mission, and the satellite data up to n equals 4 were obtained for most solar abundant helium-like and hydrogen-like ions. Now, I show this. Of course, this has been already shown by Esther. This is the kind of spectra fit between observation and calculated spectra, including all those lines up to n equals 5. This is the case of iron-25. It's a BCS spectrum. And similarly here, we have a calcium spectrum taken during the flare of May 21st as recorded by the BCS on board SMM. Now, the work this work was also used to compare synthetic spectra with other observation, in particular, as was mentioned by Esther, Inotori. Inotori also provided quite a a number of iron 25 and also iron 26 spectra, which allowed also to check the atomic parameter calculated in this case. Now, the work also was tested in fusion machines, in particular in Princeton, but also in Frascati. We had a collaboration in Francesca Bombarda, and showed a very good agreement between the calculated spectra and the observed spectra, providing very good temperature diagnostics based on the satellite line intensity ratios, showing, in fact, a very good agreement to within a few percent with independent measurements of the temperature using Thomson scattering. But what was important here was to emphasize the importance to include in the calculation all the satellite lines, high satellite lines with n larger than 2, 3, etc., in order indeed to achieve this agreement in temperature. Without neglecting those satellites would have made a difference of 25% between the electron temperature from the satellites and the independent measurements of the electron temperature. So this was a further confirmation of the powerful diagnostic capabilities of the satellite lines. So I showed this. Now, I would like to conclude my very short talk by paying tribute to Alan through his leadership, scientific insight, and also instigator of international collaboration. His work in laboratory spectroscopy theory and interpretation has provided important data and new diagnostic methods which had not been available earlier. So these topics are among the many other contributions that Alan has provided throughout his scientific career. Thank you very much, Alan.